Hello. Venu, I think you can start the session.
Yeah, sure. Thank you, Srishti. Cool. Hi, everyone. Good evening, one and all. Recording. Okay. Started recording.
Venu, I think you can start the session.
Okay. Is my voice is clear? Yeah. Hi, everyone. Good evening. Good evening.
Yeah, you are audible.
Thank you. Right. So, okay, maybe we'll wait for 1 minute or 1-2 minutes. We will start. So, if you had any questions, you can put it in the chat. I can take few questions. Yes. Good evening. Good evening, everyone. So, I see still some students are joining. Somebody saying East or West, Venu sir is the West. Thanks. Cool. Sir, can we skip DSA speed test? Yeah, maybe you can give later also. Yeah, thank you for doing this. Yeah, thanks. It's live. Yes. Yeah, good evening all. Okay, so we will start. Let me share my screen. Okay, so I'll change the view, standard view. So can you all see my screen? Yeah, so somebody asking, is this session is available in YouTube as well? Yes. So once this session is completed, so you can see the recording in YouTube itself. Right, so I hope you can see my screen.
Yes, yes, we know it is visible.
Thanks. Cool. So we will start, friends. So again, welcome to the Dynamic Masterclass on Dynamic Programming. So it is actually part 1. So this is actually part 1. So this is a very big topic. So just covering in 2.5 hours, it is little difficult. So that's why I have divided into some parts. Okay. So today we will learn all the basics things related to DP, and we will see maybe 2-3 problems, right? So because once you have a good foundations, so later you can solve any problems based on dynamic programming, right? So that is why I want make first clear all the fundamental things with respect to dynamic programming. Now, one more thing that I want to convey here, if you attend any product based company, you take any product based company, so Google, Microsoft, Amazon, any or any small level company or startup, right? So you can expect compulsory one question from the DP. So people will call in short dynamic programming as DP. Okay. So compulsory one question you can expect, friends, from dynamic programming, right? So therefore be good at this topic, right? So I will make as simple as possible this topic. So actually there is one smart approach is there to solve this type of questions. So we will discuss those approaches, right? Okay. So before I start, so for the students who are new, so I'd like to introduce myself. So I am Venu Gopal Panchumarthi. I am from Guntur district, Andhra Pradesh. So I did my BTech from IIIT Nujvid in the stream of Computer Science and Engineering. Then I did my MTech from Hyderabad Central University, and my specialization is information security, right? So I cleared both GATE with 95.6 percentile, and I cleared even UGC NET and JRF both with 99.48 percentile. So before joining at Masai, so I worked at EA Sports as a software development engineer 1. Right. So after that, I joined into Masai as a data structures algorithm instructor, and then I got promoted to senior curriculum engineer. So it's close to 1.9 years at Masai. So I'm about to complete 2 years in the next month. Right. So close to, I have handled almost 19 batches I have handled so far at Masai, 19 batches. So currently 20th batch is going on, and I thought almost all the concepts of DSA. So on this overall 19 batches, almost all the concepts of DSA I have covered. Now, a couple of months back, I have started this series as a masterclass. So in this, I have close to 5+ years of teaching experience, which means during my masters and during in bachelor's also, I used to teach, and close to in Masai and outside Masai, I have mentored 5,000+ students. Like not only on DSA, I given classes for UGC NET GATE as well for some subjects like data structures and algorithms, right? Okay. So without wasting much time, let me start the topic, that is DP, friends. Right? Okay. Now, before we start dynamic programming, this concept, so we should know, friends, what are all the different algorithm design strategies that we have. So if you given any problem, whether it is DSA or in general any coding problem you take, so you need to solve, if you want to solve that problem, first you need to write some algorithm. Right. So without algorithm, you can't directly implement the code. First, you need to write that algorithm. After that, you have to analyze that algorithm. In case if that algorithm is correct and it is optimal, then we can code that. Right. So here, while writing algorithm, so we have some standard design techniques are there, or some design strategies are there to design this algorithm. So the first and simplest one is brute force approach. Like if any problem is given, so this come to by natural to our mind. Right? Whether it can any problem, any DSA problem that you take. So natural thing that comes to our mind is simple brute force solution. Of course, it is not optimal, but easiest way that is. So which is also we can call it as an exhaustive search, where we consider all possibilities, right? So exhaustively we will take each and every possibility and we code it, and that we call it as a brute force technique. But friends, brute force technique, obviously time will take more. So we need to optimize the technique. Now, these are all optimization techniques or optimization algorithm design strategies, friends. That is, one, we have divide and conquer. Second, we have greedy. Then we have backtracking. Then we have dynamic programming. And we have something called branch and bound technique. Like that, many design strategies are there. Okay. So now I think brute force, I no need to speak much about, because you people are already aware of brute force technique. Then divide and conquer, greedy, backtracking, dynamic programming. These four concepts you should know, friends. Like before giving any interview, these four kinds of design strategies you should know. Right? Many problems that will fall under this category. Maybe if you take divide and conquer, so maybe merge sort, quick sort, or maximum sum subarray. All these problems are fall under divide and conquer. Next, if you take greedy, so we have Huffman coding is there, Huffman coding, or optimal merge patterns is there, optimal merge pattern. Like that, many problems are there. Job scheduling with the deadlines. So many such questions are there which falls under greedy. Now, if you take backtracking, so we have n-queen problem, and we have a graph coloring problem, and we have solving Sudoku puzzle. Like that, many problems fall under backtracking. Now, dynamic programming, anyhow, we will see now. Now, when you comes about branch and bound technique, so this technique, you no need to worry much about this technique, because actually this is discussed during masters. So maybe if you go for MTech, or if you go for MS, so there they are going to discuss more about this technique, friends. So there are some AA problems are there. So there are some AA problems. So where we will use this branch and bound technique. Therefore, for the time being, you no need to worry about this technique. So if you know for the first 5 techniques, they are more than sufficient to crack any DSA interview. Any DSA interview, right? Okay. Now today our main focus is on 5th one, that is dynamic programming. Right? But before we see this DP, maybe for some time, let us talk about first 4. Just kind of a revision. First one, that is divide and conquer versus dynamic programming. Okay, so first we'll talk about divide and conquer versus dynamic programming. Like when we have already divide and conquer, yeah, as I told, these all are optimization techniques. So we have divide and conquer. Why people are using greedy? Why people are using DP? Just in divide and conquer itself, we can solve all problems, right? But there are a few problems are there which we can't solve with the help of divide and conquer. So we will go for DP, friends. But maybe we'll see some basic introduction about divide and conquer. So okay, so here I will take one example. So with that example, I'll make this clear. This divide and conquer technique is okay. So we have one big problem. Let us assume we have one problem. Okay, so let us say solving this problem directly is little difficult. Okay, maybe we can take some general problem. Let us take, maybe let us say in your home, I think we all have sisters. In case those who didn't have sisters, let us assume maybe you can take some cousins or someone else. So let us say in my home, I had my sister. So now my dad decided to marry her to someone else, right? So my dad decided that, right, for my sister's marriage. So he brought some money, right? In case if you are doing marriage means definitely some money required, right? Maybe let us say purchasing the gold. My dad wants to purchase some gold to my sister. So let us say he brought maybe 4 lakh rupees loan. let us say he brought 4 lakh rupees loan. Okay, from someone else. Okay, so let us say that fellow who given 4 lakh rupees to my dad. So he given everything in terms of 2000 rupee notes. 2000 rupee notes he given. Okay. So if he given everything in terms of 2000 rupee notes, so total how many notes he will give? In case if he is giving 4 lakh rupees loan means, obviously he will give 200 notes. Total 200 notes he will give, big bundle of 200 notes, where each note is of 2000 rupees. Now he will bring to the home. Now he given to me to count it. Now what I'll do, I'll keep all these 200 notes in my hand and I'll start counting one by one, right? So I will count 1, 2, 3, 4. Let us assume somewhere if I went to 49, like I got struggle, assume counting is failed. Then what I'll do, again I'll go for the 1, 2, 3, 4. After reaching, let us say 99, assume my counting, some mistake is happened. Then what I do, again I have to go start from 1, 2, 3, 4, 99. Somewhere after going to 188, let us say I again failed. It usually happens, right? So rather than taking all the 200 notes one by one, maybe what I can do is, so I can divide these 200, total 200 notes are there, right? So let me divide all these 200 notes into different chunks. Okay, so different chunks I will decide just to make the counting easy. So maybe I will divide total 200 bundle notes into different sets. Maybe let me call this is set 1 and set 2. I don't know, friends, exactly how many how many notes are there. I have just divided. Okay, so let us assume after dividing, I distributed randomly these 200 notes. Now, first here I got 45. Now, see, counting 200 is really difficult. Therefore, what I will do, I will divide, and after dividing into 4 sets, I got it is as 45. Next, let us say this set I have counted. Now I got this as 55, right? Next set I have counted, and let us say I got this as 50. I got it as 50. Now S4, is it required to count? Tell me, set 4. So can I directly say to my dad, so dad, total we have 200 notes. Can I say directly without counting? Because here 45, 55, 100, 100. Next this is 50. But here I did not count it. So can I say directly without counting how many notes are there in set 4 to my dad, that these are total 4 lakh rupees? No, I should not do like that, because I might not have trust on the person who given money to my dad. Therefore, what I need to do, because this is money now, right? Therefore, I have to count this also. For example, after counting this S4, let us say if it is got 50, then I can say that my dad, yes, total they are 4 lakh rupees. So now we can go and we can purchase gold to my sister. That is how I can say. Now see here, taking all the 200 notes one by one is little difficult. That's why what I have done, bigger problem, I have divided into small problems. See here, what is the bigger problem? Counting 200 notes, right? Total 4 lakh rupees, I have to count it. So total 200 notes, bigger problem, I have distributed into small problems. Maybe counting all 45 notes, or let us say it's difficult for you. Further, you can break down. So till how long I should suppose to break down? So till you need to divide this problem such a way that to solve it will be easy. So like that, I will divide, friends. After dividing, what I am doing, I am calculating, or I am solving this problem. After solving, like problem, I have divided the problem into small problems. I have solved these small problems. Solving means here counting. I have counted all this. After that, I am again adding all the solutions. Bigger problem, small problems, and small solutions. And I am adding small solution to a final solution. Problem is counting all the notes. Solution is I need to say total 4 lakh rupees or not. So big problem divided into small problems, and I have solved the small problems, and I have added solution to the small problems, so that I got a final solution. That is the concept of divide and conquer. So now here, if you see, friends, let us say I am counting this set S1. So when I am counting this set 1, so maybe my mother also can count the second set. There is no restriction that when I'm counting this set 1, even my mother also can count this. And at same time, my sister also can count this. Same time, my father also can count. Therefore, here, solution of one problem is not depending upon other problem. Solution of one problem is not depending on the other problem. Getting now? So here counting, I can do parallelly. My mom can do, my sister can do, my dad can do. So all are independent problems here. All are independent problems. Now, when same thing comes to the DP, DP, what is the difference is here? Here also problem is there. Here also we have a bigger problem. Here also we have a bigger problem. Now this bigger problem, we will divide it into small problems. Small problems. Okay. So maybe let us take problem number 1. Okay. Second, third, fourth. In DP, what will happen is, so whatever the solution of this problem, that solution we will use here. Here, the solution we won't use, friends. Independently, it will go. But in DP, what will happen? Bigger problem, we will divide it into small problems. Now, solution to one problem will help to solve the second problem. Solution to this problem will help to solve the another problem. So that is nothing but there is a concept called overlapping subproblems are there. Overlapping subproblems. Like when I explain this concept, I'll talk again in DP. So this is overlapping subproblems. So after some time, I will discuss this concept. There's a fundamental difference between divide and conquer and DP. So in divide and conquer, all are independent. Whereas in dynamic programming, solution of one problem will be helps to solution to other problem. That is the concept in DP, friends. Again, don't worry if you did not understand, like theoretically, when I take problems, it will be clear. It will be clear. Okay. So this is the story of divide and conquer and DP. Now, in between divide and conquer and DP, okay, we have greedy, friends. We have greedy. So now let's understand that greedy also, so that we can happily continue with the DP. So divide and conquer, greedy, DP. Between these two, we have greedy. So for some time, let's talk about greedy also. So as I told, when we have already greedy, so why DP? Why DP? Why can't we use greedy like for every problem? For every problem, why can't we use greedy? Maybe I will take some examples where this greedy can fail, friends. So maybe one problem is, let me take a very famous problem, that is fractional knapsack problem. Like what this problem says is, so knapsack means bag, a carry bag you can assume. Carry bag which we will take to purchase some items, right? Okay. So for this knapsack, we have a capacity. So the maximum capacity of the knapsack, let me take as 20 kg, which means we had a carry bag which can hold a maximum of 20 kgs of weight. And here I have given total 3 items. Item number 1, item number 2, item number 3. Let me call objects. Okay. Now, for every item, 2 things are associated with that item. Those are, one is profit, second is weight, which means for every item, 2 things that are associated. One is profit and another is weight. So if you take the first object, so profit, if I get 25 rupees, if I take first object, I will get 18 rupee profit. If I take the second object, I will take the 24 rupee profit. If I take object 3, I will get 15 rupees profit. Now, final objective of this problem is, so you need to take as many objects as you want. So, but these objects, let us say you have taken 2 objects, maybe object number 1 and object number 3. You can take any objects, no problem at all. But only concern is, so it should not exceed the maximum weight of the knapsack. That is the only concern. Next, you have to get a maximum profit. That is the objective of this problem. So you need to bring the maximum profit. Okay. So since it is greedy, so let me think also in the greedy way. So in the greedy way, right? So first what I will do, first what I'll explain, I am more greedy about profit. So case one, what I will do is, so I am more greedy about profit. So if I am more greedy about profit, then what I will look, I am going to take the object which is having the highest profit. Therefore, which object I will choose, friends? O1, O2, O3. So which object that I'm going to choose first, since I am more greedy about the profit? So obviously the item which is having the more profit. So now see P1, O1, O2, O3. Obviously, first object is having the highest profit. Therefore, let me take first object number 1 completely. Okay. I had a capacity 20 kg. Remember, my knapsack is maximum 20 kgs. If you can take object 1, okay, let me write profit also. How much profit that I'm going to get? First object you are taking completely. Therefore, you will get a profit of 25 rupees. 25 rupees. Right? Then once if you taken the object number 1, its weight is 18 kgs occupied. So now you are left with only 2 kgs. only 2 kg. Next, once if object 1 is chosen, right? Now I have O2 and O3. Next also I want to choose a object having the highest profit. Now O2 and O3, O2 had a highest profit because it is 24, it is 15. Therefore, now let me choose object number 2. But object number 2 has the capacity of 15 friends. But I don't have that much capacity. I have only 2 kgs remaining. Therefore, available 15 kgs, I will choose only 2 kgs. 2 kgs. So how much amount the profit that I will get? I will choose that much only. So which means what is the profit that you will make here? Total you had 15 kg. That is object number 2. Object 2 total 15 kg. But out of 15, let me choose only 2 kgs. And what is the profit of O2? 24. So overall, this much amount that you can make if you go more greedy about profit. Now, can you help me? What is this value? What about this value, friends? So 25 plus, so 2 by 15 into 24. So what is 2 by 15 into 24? Let me try to calculate. 2 by 15 into 24. So roughly I'm getting 3.2. So 20. So this is 3.2. Now 25 plus 3.2, which is 28.2 rupees profit that I'm getting. Don't worry if they are in points, it's okay. Next, let me go for, in case if I am more greedy about profit, I am getting 28.2 rupees, friends. What if I more greedy about, let's say, more greedy about weight? If I more greedy about weight, right? So then I am going to, if I am more greedy about weight, which means I will be more concerned about weight. If I am more concerned about weight means I am going to choose an object which is having a less weight. So I will choose an object which has less weight. Why I am choosing object have less weight? If I choose an object of less weight, I can pick more objects. Simple common sense that is. If I choose an object which is less weight, I can choose more objects. Correct, na? Okay. Now here, if you see available all the objects, obviously object number 2 is having less weight. Therefore, first I am going to choose object number 2. Object number 2 completely I will choose, friends. So that I will get O2, right? 24 rupees profit I will get for the first time. Now, but I had a capacity 20. Please remember this. Once if you choose object 2, out of 20, 15 is already occupied. Now you are left with only 5 kgs. 5 kgs, right? Next, what is remaining? O1, O3. Among these two, O3 had less weight. O3 has less weight. But I can't take completely O3 because I have only 5 kgs left. But its weight is 10. What I will do, out of 10 kgs, I will choose only available capacity. That is 5 only I will choose of O3. Okay. And now how much profit that I can expect here? So 5 by 10 into what is the profit that I will get if I choose object 3? O3 if I choose, I will get 15 rupees of profit. I will get 15 rupees of profit. Now, what is this value, friends? This is 7.5. So because 15 into 5 is 75. So 7.5 plus 24. So which is 31.5. Okay, so you people think that, okay, if I go greedy about profit, it is giving less profit compared to greedy about weight. So you might come to a conclusion that I will go for greedy about weight. But that is not always true, friends. That is not always true. That is not always true. Okay. Next. If I am more greedy about, what actually, by doing some research, what we came to know about is, if I go greedy more greedy about profit by weight ratio. If I go greedy about profit by weight ratio, let me explain here. What will happen? Means I will compute profit by weight ratio. After computing profit by weight ratio, I will choose an object which is having the more profit by weight ratio. Now, if you check here, which object having the high profit by weight ratio? O1, O2, O3. First, object number 2 is having the more profit by weight ratio. So next, I am choosing O2. Just a minute. O1, O2, O3. Okay. So greedy about profit by weight ratio. So profit by weight ratio, highest is having O2. After that, next profit by weight ratio is O3. O3 have taken for case 2. O2. I think which is same as O3, right? Greedy about weight. Highest weight is O2. Sorry. I think we have done a mistake. Okay, it is mistake, friends. Wait. Actually, if I go more greedy about weight means first I'm going to choose the less weight object, which is O3, right? First I have to choose O3. Sorry, this is my mistake. Okay, so this comes here. So it's my mistake. So this comes here. Here is greedy. So first I need to choose an object which is having less weight. Less weight object is O3 now first. Therefore, I will choose O3 completely first. If I choose O3 completely, then what will happen? So this will be 20 out of 20, right? So you have chosen O3 completely, so that now you are remaining with the 10 kgs. How much profit that you will get if I go more greedy about weight here? So first to O3 profit is 15 rupees. So 15 rupees plus next. After that, which object is there? O3 you have chosen because it is having less weight. Next, which is having less weight? O2 is having next less weight. So O2. But O2 I can't choose completely. Why? You had only 10 kgs remaining. But O2 weight is 15. Therefore, out of 15, you are going to choose only 10 kgs. So 10 kg. Now 10 by 15. So into O2. So which is nothing but 10 by 15. What is the O2 profit? O2 profit is 24. Now can you help me? What is this value? 240 divided by 15. So what is this sum? 240 divided by 15. 240 divided by 15, which is 16 plus 15, which is 31, friends, which is 31. Okay. If I go greedy about profit, I'm getting 28 rupees. If I go greedy about weight, 31 rupees. If I go greedy about profit by weight ratio, I am getting 31.5 rupees. O2 had highest profit by weight ratio. After that, greedy had next O3 have next highest profit by weight ratio. Therefore, if you want to solve the fractional knapsack problem, you should pick the highest, okay, profit by weight ratio first, right? So this is one interview question. If they talk about fractional knapsack. Now, same technique, I will try to apply even 0-1 knapsack problem also. Now, let me take one 0-1 knapsack problem, right? So what I came to the conclusion from fractional knapsack, if you want to get a maximum profit, you should go for first high profit by weight ratio first. That is the conclusion that I have made here. High profit by weight ratio. You should go, right? Now, let me apply to even 0-1 knapsack problem also. Now, this is most important here. Like, what is the difference between fractional knapsack and 0-1 knapsack? In fractional knapsack, they are allowed to take some part of the object. Whereas in 0-1 knapsack, so you take it or don't take it. Only two choices. Only two choices are there. You take that object completely, you take or don't take. Don't take. Okay. Only two things are there. So fraction is not allowed. Fraction is not allowed. Not allowed. That is the concept of 0-1. You take means 1. Don't take means 0. 0-1 knapsack, right? Now, again, from the previous greedy, I came to a conclusion that highest profit by weight ratio I have to choose. Now, if you see here, knapsack capacity is 10 kg. So profit 210 and weight 1. So what is the profit by weight ratio? First, this is 2 kg. Whereas object number 2, this is 1. Right? Profit by weight ratio means. So P by W. So P by W profit by weight ratio. So 2 by 1, this is 2. Next 10 by 10 is 1. So now what I'll do? Now I will go and choose, obviously, which object as per the greedy I'm going to choose. High profit by weight ratio. No, so its capacity is 10 kg. So its capacity is 10 kg. As per the high profit by weight ratio, first I'm going to choose object number 1 first. So first I'll choose object 1. So first, if I choose object 1, its weight is 1 kg, which means, so 1 kg is occupied. So 1 kg is occupied. Okay, so let us say total this is 10 kg. Total this is 10 kg. Out of the 10, 1 is already occupied by O1. Now next I am remaining with 9 kg. 9 kg. Now, can I choose this object too? You can't choose because its weight is 10. Its weight is 10 kg. But 10 kg you can't keep here. But can I take 9 out of 10? No, you can't take. You can't take 9 out of 10. Why? Fraction is not allowed. That is the problem in 0 1 knapsack. So what is the maximum profit you will get it here? Only 2 rupees you will get it. If you go for high profit by weight ratio. If I go for high profit by weight ratio, this is what tells by greedy. So what greedy tells? High profit by weight ratio, you can choose. But here clearly greedy is failing. There is another way where you can get more profit. What is that way? I can directly choose object 2. I will get 10 rupees profit. I will get 10 rupees profit. So here we are not choosing high profit by weight ratio. Therefore, here clearly greedy fails. So here clearly greedy fails. So in interview, they can ask a question, tell me why greedy fails. So can you give an example where greedy is failing? So there you can tell this example. Okay. Next. Right. So please make, I will share these notes at the end of the class, but please take a note of this. Okay. Now, again, I'll take one more example where clearly greedy will fail. So in this problem, clearly greedy is failing. Maybe next problem I'll take. So here we have a graph. Assume total there are 6 cities are there. City A, city B, city D. So let me call this city as a source. Okay. And I will call this city as a destination. Now I want to travel from source to destination, and these all are the 6 cities. Let me take city 1, city 2, city 3, okay, city 4, city 5, total 6 cities I am going to take, right? Now we want to travel from one city to another city. Let us say this is the distance, which means 10 kilometers, 4 kilometers, 25 kilometers, like that. Now I want to find a optimal way, which means I want to travel with the less distance. So you need to figure out. So again, I'll try to apply greedy here. Here, if I think in terms of greedy, right, what I am going to choose first, future, I am going to think at this point of time, who will give the best value, that I am going to choose. That is what greedy tells. Right now, when I am at A, so I have 4 options that are available. I can go to city 2 with 10 kilometers. I can go here 2 kilometers. I can go 9 kilometers. I can go to another city 4 kilometers. 4 possibilities are there. So if I think using like a greedy, obviously I am going to choose at this point of time who will take me to the another city in a less distance. So obviously I'm going to choose A to D because it is taking to 2 kilometers only, whereas remaining is 10, 9, 4. So definitely if you go for greedy, if you choose in terms of greedy, so first I will choose A, then I will go to D. How much distance? 2 kilometers. 2 kilometers, let us take. Now from D, ultimately I need to reach to F. From D, there is no other option. Only one option, that is D to F is 25 kilometers. 25 kilometers. Now finally, how much distance that I travel from source to destination? If I go about greedy, total 27 kilometers that I have traveled. But is it really the optimal distance? No, it is not optimal distance. I will take another path, that is first I will go to A to E. I will go to A to E with 9 kilometers. From E, I can go to F with 3 kilometers. So I can able to travel in 12 kilometers only. 12 kilometers only. Now maybe if you choose another 4 plus 6, 10, 10 is 13. There are different ways are there. So therefore, if you choose a greedy, it is not going to work here. Clearly greedy is failing here also. Because I had a best way. So how I am able to solve this? So we have one DP algorithm, that is Floyd-Warshall algorithm. So Floyd-Warshall algorithm is that we will see when I discuss about problems on DP. Maybe part 2, I might cover this question, right? So there is one algorithm which works on DP, dynamic programming principle, that is Floyd-Warshall algorithm, which is finding distance from all pairs, from any pair to any city to any other city, you can find the distance, okay, which is in n cube time, but anyhow, that we'll see little later. So here my intention is to convey where clearly greedy is failing. So this is the case where clearly greedy is failing. Right? Okay, cool. So now so far I have covered, friends, all the theory of greedy, DP, all these things. Now we don't waste much time. Let's directly take some problems and we will solve. Okay. So first question is like, how should I identify, yes, this problem can be solved with help of DP or not? So we have seen DP and all the theoretical stuff, but tell me, if I give any problem, how should I know? Yes, I have to apply DP to this question. How should I know? Yes, I have to apply DP to this question. There is a smart trick is there to identify. So if any problem containing some optimization terms, so listen carefully, friends. If any problem contains some optimization terms like minimum or maximum or okay, smallest or largest, like some optimization terms. If you see in this problem, maybe you can think of okay, DP. Next, another trick is usually we write some brute force solution, right? Usually we do write some brute force solutions, correct? So after writing brute force solution, try to analyze its time complexity. So if you find the time complexity of exponential time, so if you find out the time complexity is exponential time complexity after analyzing this brute force solution, and you want to convert that exponential into a polynomial time complexity. So polynomial time complexity, top polynomial time complexity. So we will use DP, friends. We will use here DP. So like what exactly meant by exponential and what exactly meant by polynomial? Okay. So exponential time complexities are like order of 2 power m, or order of 3 power m, or something like order of n power m. All this comes under exponential time. Now, after analyzing this brute force solution, if any problem time complexity comes into 2 power n, 3 power n, then you can immediately apply DP here. So when you apply DP, what happens is time complexity comes under in a polynomial time. Polynomial is nothing but order of n square or order of n cube, etc. So this is polynomial. So maybe in general, if you want to say this is order of n power k, or no, order of a power n, okay. So where a is greater than 1 or a is greater than 0, greater than 1, like, and n is greater than or equal to 1. This is general exponential polynomial. So sorry, this is polynomial, right? So order of n power k, where k is greater than or equal to 0, like n square, n power 1, and n square, like that, friends, like that, right? So cool. Now first question, very famous question that we will see: finding nth Fibonacci number. Now, any DP problem you take, so first what we will try to do is, we will try to write a brute force solution. Mostly these brute force solution, we will use recursion. So the prerequisite of DP is recursion. So you should know recursion, friends, to solve any DP related questions. First, we will write the brute force solution. Then we will analyze the time complexity. If the time complexity comes under exponential, then we will see the DP solution. That is the idea for any problem. DP solution we'll see. First, we will write a brute force solution. After that, we will analyze its time complexity. If the time complexity is exponential, then we will write DP solution. Okay. Now, so the first question is, find the nth Fibonacci number. So let me define what is meant by nth Fibonacci number. Okay, so here I'll take some numbers. So I'll define what is nth Fibonacci means. So here I'll take n value. F of n. So n value, let me take 0, 1, 2, 3, 4, and so on, 5, okay, and so on. Okay, if n is equal to 0, 0, 1. So these two are basics. Okay, I mean base conditions. Now, so general Fibonacci of n is equal to, if n is equal to 0 or n is equal to 1, then its value will be n only. Okay, if n value is greater than or equal to 2, then it is f of n minus 1 plus f of n minus 2, n minus 2. So this is the Fibonacci definition, friends. So this we can call it as a recurrence relation also. So this another name of this is recurrence relation. Okay. Now if Fibonacci of 0 is equal to 0, so let me write Fibonacci of 0 is equal to 0. Next, Fibonacci of 1 is equal to 1. 1 is equal to 1. Now, what about Fibonacci of 2? Fibonacci of 2 is nothing but as per the definition. So, Fibonacci of 1 plus Fibonacci of 0. So, we know already Fibonacci of 1 value. So, Fibonacci of 1 is equal to 1. And what about Fibonacci of 0? Which is 0. So, 1 plus 0, its value will be 1. What about Fibonacci of 3? Previous two terms sum. So 1 plus 1, that is 2. Fibonacci of 4 is nothing but previous two terms sum, 3. Fibonacci of 5 is 2 plus 3, 5. 5. Now what about Fibonacci of 6? Fibonacci of 6. Can you type here? Fibonacci of 6 is how much? Simple. So previous two terms, it's a sum, 3 plus 5, 8. So like that you can derive, friends. You can derive. Okay. Now first, here if you see, you can see some kind of recursion is applying. Same function you are calling again and again with a smaller values. So in my recursion live, if you attended my recursion YouTube live, so there I have explained clearly about recursion. If the same function you are calling again and again with smaller size of inputs, so then that's called as a recursion. So I have already written the recursive solution here. I have already written the recursive solution here. So simple. This function Fibonacci, it is taking n. And this is called the base condition. If n is equal to 0 or n is equal to 1, whatever that n that we have to write, else we have to call same function with n minus 1 plus n minus 2. Now, if I call Fibonacci of, let me write Fibonacci as f. So let me write Fibonacci as f. Okay. Now, if I call the value maybe 5, for example, if I call the value of Fibonacci of 5, so what is the output that I'm expecting? 5. Let us see. Same code. Let's try to do that dry run. Now, n value right now is 5. So, is n is equal to 0 or n is equal to 1? No. Then, what I'm going to call? I'm going to call two things. That is return. So, Fibonacci of n minus 1, that is Fibonacci of 4 plus Fibonacci of 5 minus 2, that is 3. So first, what will happen? This is going to get executed. After that, this will go and get executed, right? So now I am calling Fibonacci of 4 again. So first time I am calling 5. So later n will be coming. Now again, this base condition will false. So let me call again two things here. So that is return. So Fibonacci of 3 plus Fibonacci of 2. So these two will not called right now. That is the property of recursion. First, this is going to get executed. So next I am calling Fibonacci of 3. So when I call Fibonacci of 3, again base condition will false. So these two cases are going to get executed. Okay. So this is again return Fibonacci of 2 plus Fibonacci of 3 minus 2, that is 1. Now I'm going to call with 2. Now when I call 2, again base condition will false. So these three are going to get executed again. Now if I call again, this is return Fibonacci of 2 minus 1, that is 1, plus return. Okay, return is not there. Fibonacci of okay, 2 minus 2, that is 0. Now it is interesting. Now if I call Fibonacci of 1. Now see here, it is touching the base condition, right? So it will, whether it is n is equal to 0, it will return 0. If n is equal to 1, it will return n, right? So here, now n is equal to 1. Now this base condition true, right? Now Fibonacci of 1, it will try to return a value 1. Okay. Fibonacci of 1 is now 1. Now when I call now once it is completed, next term will get executed. Now it is going to return 0. 1 plus 0, 1. And that return will be to return to whom? Whoever called that function, to that it will try to now return a value 1. Now Fibonacci 2 had got a value 1. Next I am calling Fibonacci of 1. So I'm not writing here. Okay. Now again, when I call Fibonacci of 1, okay. So now this base condition true. So now it will try to return a value 1. Now Fibonacci of 1 is 1. Fibonacci of 2 is 1. 1 plus 1, that is 2. Now that 2 will be returned to whom? To the caller function. So Fibonacci of 3 now getting a value 2. Okay, once it is completed, now let me execute Fibonacci of 2. Now, when I call Fibonacci of 2, so same thing is going to get repeated. Now, when I call Fibonacci of 2, so whatever this structure, because see, already Fibonacci 2 called, right? So same thing is going to get repeated there also. So let me try to add that. So same thing is going to get executed again. Okay, so now let me write little left, right? Now I'm going to call again Fibonacci of 2. So this Fibonacci of 2, same only. We have already seen now. So here I'm calling Fibonacci of 2, Fibonacci of 3 plus Fibonacci of 2. So since this Fibonacci 2 is already there, right? So same thing will becomes here. Same thing will becomes here. When you call Fibonacci of 2, so you are going to get a value. We are already know Fibonacci of 2 is receiving a value 1, right? So when you call same Fibonacci of 2, of course it is going to return that value 1. Now therefore this Fibonacci of 2 now receives a value 1. So this is 2 plus 1 and the 3 will be returned. To whom it will return? Whoever the function is called, that function is going to get a value now 3. So Fibonacci of 4, now it is going to get a value 3. Right? Okay. Therefore, finally, Fibonacci of 4 is getting a value 3. So once it is done, next Fibonacci of 3 will be called, right? So now when you see here, friends, if you see here, already Fibonacci of 3 is getting calculated. Therefore, same thing, one more time it will repeat here. One more time it will repeat. So let me write it little left side. So if you see here, again, I am calling here Fibonacci of 3. So when I call Fibonacci of 3, I'm not writing again because just to save some time. So whatever this Fibonacci of 3, that will becomes here. Therefore, let me take its screenshot. Okay. So Fibonacci of 3, right? Okay. So this one will comes again. So I'm just copying and I'm pasting here. So same thing is going to get here again. Fibonacci of 3. Okay. So by the time, what is returning Fibonacci of 3? 2, right? So when you call this Fibonacci of 3 also, so same thing will be get executed. Now it is going to return a value 2. Now 2 plus 3, that will be 5. And 5 will be finally returned to the Fibonacci of 5. So this Fibonacci of 5 now will return the 5 to the caller function. Now see, that is what we are expected, right? If you call 5 we are getting. Simple recursive solution. Now here the takeaway of this code is, understand carefully, 2 things that you can observe here. Those are the very important with respect to the dynamic programming, friends. So first one is overlapping subproblems. Overlapping subproblems. Second thing is optimal substructure. So these 2 terms you need to understand. Optimal substructure. So what is meant by overlapping subproblems and what is meant by optimal substructure? So first let us talk about overlapping subproblems. Now my aim is to find out Fibonacci of 5. So when you're trying to find out Fibonacci of 5, I have to compute Fibonacci of 4 and I have to compute Fibonacci of 3. So during the process of computing Fibonacci of 4, so somewhere you have computed Fibonacci of 3 value that you have already computed. Now, just one time, if you compute Fibonacci of 3, it is not going to helpful. Why? Here also, again, you have to recompute this Fibonacci of 3. See, when you are calling Fibonacci of 4, you are computing for the first time, Fibonacci of 3. But again, also here, you are recomputing the second. Next, under f of 3, if you observe, here, for the first time, you are computing Fibonacci of 2. Just the first time, if you compute, it is not helpful. Again, also here, you are trying to compute. Okay, here itself, on the left-hand side itself, you are computing 2 times Fibonacci of 2. But if you see, right hand also, again one more time you are computing. So therefore, same problem again and again you are computing. So that is nothing but a overlapping subproblems. These subproblems are actually overlapping, friends, which means I have already done, but again and again I am doing. So that is the meaning of overlapping subproblems. Okay, first point is clear. Then what about second point? Optimal substructure. Optimal substructure. Understand the optimal substructure carefully, friends. Let me put it in very simplest way. Optimal substructure. See here, what is my bigger problem? Finding f of 5 is my bigger problem. Now this bigger problem, I have boiled down into small problems. That is, you first find f of 4, then you find f of 3 and add these two. But again, f of 4 is the bigger problem. So to find f of 4, I divided into f of 3, f of 2. So you first find f3, f2 and add these two to get a f4. But again, f of 3 is a bigger problem. So I boiled down into f of 2, f of 1. Find f of 2, f of 1, then add this, you will get f of 3. But again, f of 2 is a bigger one. So I divided into f of 1 and f of 0. You find the solution to these two and you add to get a solution of f2. Then similarly, f2, f1 you add, you will get f3. Similarly, add f3, f2, you will get f4. Like that, f4, f3 you will add, you will get f5. So solution of small problems. See, we have smaller subproblems. Optimal substructure meaning is we have smaller subproblems. Initially, we have a bigger problem. Bigger problem, we divided into small problems. So we have a bigger problem. We have a bigger problem. And these bigger problem, we divided into smaller subproblems. We divided into smaller subproblems. Smaller subproblems. And now, solution of these subproblem, solution to this bigger problem is combination of solution of these smaller problems. So, solution of these bigger problem, solution of this bigger problem is solution of these smaller problems. So, this we can call it as an optimal substructure. Right? Is the definition is clear, friends? Is the definition is clear? So, optimal substructure means solution of smaller problems will helps to a solution of bigger problem. So that is optimal substructure. So if any problem containing these two terms, first one is overlapping subproblems, then solution of smaller problem is helping to solutions of bigger problem are you getting from solution of smaller problems, then that we can call it as a optimal substructure. So if any problem containing these two things, then blindly you can apply DP. Blindly you can apply DP. Okay, if any problem is having these two conditions or these two things, then you can blindly apply DP. You can blindly apply DP. Okay, sir, what exactly this DP is? Now we came to know, okay, when these two arises, we have to apply DP. Now let me talk about DP now, and then I will convert this code into a DP code. So first, let us see what are the types of DP. So basically, we have two types of DP. One is called as a top-down DP. Second is bottom-up DP. Now, top-down DP contains recursion plus top-down DP contains recursion plus a new term that I'm going to introduce here, that is memoization. Memoization. Okay, I'll talk about in some time. Okay, next, bottom-up DP. Now, bottom-up DP contain again two things. One is loops plus memoization. So if you see in two things, there is a one common. Two types of DP if you observe. So one thing is common, friends. What is the common thing here? What is the common thing? So the common thing is memoization. The memoization is common. Here it is recursion and here it is loops. Any recursion program, you can convert into loop. Any loop, you can convert into recursion. That we already studied. Right? Then we should know about like what is exactly meant by memoization. So now again, I will go to the previous slide and I will talk here. What is exactly meant by memoization? Now, see here, first time I am computing f of 1. First time I am computing f of 0. Here also, first time I am computing f of 2. First time I am computing f of 3. This is computing second time. Second time I am computing f of 1. First time you have already computed. Now here, first time I am computing f of 3. Now if you see this f of 2, this is second time. Where you computed first time? Here. So any function or any smaller problem, for the first time if you are computing means, then store that solution in a table. So what I'm saying is any sub problem, listen carefully my statement. These are all the sub problems. Okay. This is the only main problem. All these are called as a sub problems only. This is the main problem, bigger one. And all these are, I'm going to call it as a sub problems. So for the sub problems, if you are finding out for the first time, then you store that result in form of a table or an array. Why I have to store? Because second time when you want to compute that sub problem, don't waste the time, because that you have already computed. So directly you take that value without computing. So let me write it here. Let me write it here. Okay. Sub problems. So see friends, so let us say when you are finding the solution to the sub problems for the first time, then store that solution in a table or an array. Table or a array. Okay. See, when you are finding the solution to the sub problem for the first time, then store that solution in a table or array. Next time onwards, if that sub problem again repeats in case next time onwards, if that sub problem again repeats, then directly, then solution, then you can take its result directly from the table or array without computing. That is important. Without computing. Okay. This is the important point, friends. Because we are wasting time for a computing, we are wasting time now. So when you are finding solution to the sub problem for the first time, then store that solution or store that result, not solution, friends, store that result. Okay. Because at the end we need result, right? So store that result in a table or an array. I will tell you where to use table, where to use array. Next time onwards, if that sub problem again repeats, okay, then you can take its result directly from the table without computing, which means don't waste the time again for the computing. This is unnecessary, because when you have already a solution, why to waste the time? Tell me. You can take directly from there. You can directly take there. Okay. Okay. Sir, how can we take the result? I'll explain. Okay. So without computing, you can directly take that result. I will tell you, friends, how to take. Okay. I'll take this problem only and I will explain. I'll take this problem only and I will explain. So I'll take the next slide. So if you remember, we have two things, top-down DP and bottom-up DP. In top-down DP, I told recursion is compulsory, plus memoization. So memoization means storing the sub-problem results in a table, and whenever you require, you take those results. Simple. Okay. So I have taken already the code that is available. I have already taken the code that is already available. So this is nothing but a recursion code. I hope you all know. Now let me take the same recursion code here. Let me take the same recursion code, and here I will take one array. Result array I am going to take. Result array, and I will take its size as 100 or 1000, whatever. And I will set all its values to -1. See, here you might have a doubt, sir, how much size that I should supposed to take the result? Is it 100 or is it 100,000, 10,000? Any size you can take, friends. It depends on the question. Maybe in the problem, if they are saying n value, maybe in the given question, if they specify, okay, so your maximum n is say 1000, for example. If they mention like this, then you can create a result array of size 1000, of size 1000. Now here, small change thing you need to do here. Same only, what extra change that you have to do? See where exactly recursion call is happening. So this is if statement, and else statement recursion call is happening. Correct? In the else statement, recursion call is happening. Before recursion call is happening, you just need to write one statement. What that statement is, what that statement you need to write is, if result of n is equal. See, initially you have taken a result array and you have taken its size as 100, whatever that n value. Okay, 1000 or 1000 you can take, no problem. And you initialize all these values with -1. So initialize, set all values of result array to -1. Why -1 only? You take any value, friends. Any value which is not involving in this Fibonacci series. Maybe you take -2, you can take -10 also. Some -1. If I take -1, so that you see anywhere, are we getting -1 in this table? No. That is why I have taken -1. You take -2 also, no problem. You take -2 also, no problem. So here I have taken -1. Here, result of n is not equal to -1. Okay. So what I will do, I will simply return result of n as my answer. Otherwise, here, okay, after writing, I will explain these two clearly. Result of n is equal to Fibonacci of n minus 1 plus Fibonacci of 2. Now let me explain this code. Let me explain this code. Two things that I have done here. As it is, I have copied my recursion code. One change that I have made is, so I am checking before calling this recursion call directly, I am just checking whether that value is already available in my array or not. If that is not there, then second step, what I am doing, I am storing this result. This is the second change that I am doing. Two things, right? Now let me explain this code. Let me explain this code. Okay, so we have already a result array. So let me draw this result array, which we have already created. 0, 1, 2, 2, 3, 4, 5, 6, and so on. Okay, let us say, friends, I let n is equal to 100. Let n is equal to 100. So I have created a size of 100 array. 1D array I have taken. So this is 0, 1, 2, 3, 4, 5, 6, and so on. Let us say this is 99. This is 99. And the name of this array that I have given as result array. Result is a name that I have given to this array. All values I am setting it -1. -1, -1, -1, -1, -1, -1. All these values that I have set with -1. Okay, very good. Now, I am calling again Fibonacci of 5 only. I am calling again Fibonacci of 5 only. Now let me see, am I getting this much bigger tree or not? I have taken same example, same code. I have converted into small changes I have done, and I am calling. If I get all these many calls, then that is wrong. But let me see I'm getting or not. Okay. Now understand this carefully. So again, now n is equal to 5. Now what I am checking first time, I am passing n to 5. Is 5 is equal to this? No. Now my result of n is not equal to -1. I'll check. What is my result of 5? Is it equal to equal to -1? Check here. Result of n is not, if it is not -1, then straight away I will return this value. But it is not -1. It is in fact equal to -1. Therefore, this condition will be false. If it is not -1, then I will straight away return that value as a result. But that is not true. Then what I am doing here, if you observe carefully, I am calling return. So what I am calling, I am calling two things I am calling here. Now understand these two things. So I am calling return result of n is equal to result of, what is n value? 5. So result of 5 is equal to, I am calling Fibonacci of n minus 1, that is 4, plus Fibonacci of n minus 1, that is 3. This is what I am calling, friends. So when any function call is happening, first left hand function call will get executed first. So now I am calling n. Again, Fibonacci of 4 I am calling, which is n is equal to 4. Next function call. Now this is false. Now check carefully. Is my result of 4 is not equal to minus 1? No. No, right? Result of 4 is in fact equal to minus 1. Therefore, again, I'm going to call this statement. So when I call this statement again, what is happening? What is happening here? So return result of 4 is equal to Fibonacci of n minus 1, which is 3 plus Fibonacci of 2 I am calling. So first Fibonacci of 3 will get executed. Next, now in this function call, I am calling 3. Now this is true? No. Is my Fibonacci of 3 is not minus 1? Yeah, it is minus 1. But if it is not minus 1, I will return that value. But it is minus 1 only. Therefore, this is also false. Then again, else statement is going to get executed. Now in the else statement, what are the things that are present here? So this is n I am calling again. Okay. Now when I call this time, now, okay, now Fibonacci of 3 I am calling, friends. Now when I call, I think result of 4 is equal to, yeah. So when I call Fibonacci of 3, false, this is going to get executed. That is return. Okay, so result of 3 is equal to, so what I am calling Fibonacci of 3, when I'm passing 3, Fibonacci of 2 plus Fibonacci of 1 I am calling. Okay. Now at this point of time, now again, n value will be 2. Now check, is Fibonacci of, first of all, is it true? No. Fibonacci of 2 is not minus 1. No, it is minus 1. This is also false. Okay, so this is also false. Then else statement I'm going to get executed. Now when I'm executing else statement, now see. So again, I'm calling return. So result of n. What is n at this point of time? 2. So result of 2 is equal to what I'm writing again, Fibonacci of 2 minus 1, which is nothing but 1. Plus, it is interesting, friends. See here. So Fibonacci of 1 plus I'm calling Fibonacci of 0. Okay. First Fibonacci of 1 will get executed. Now see from now onwards. So now again, n value will be 1. So when n is equal to 1, is the base condition true, right? When n is equal to 1, I am straight away returning that n value, whatever that n that I am returning. Therefore, Fibonacci of 1, this value, I am going to return it as a 1. Okay. Plus next time, when I am calling Fibonacci of 0. So when I call Fibonacci of 0, base condition is true. So 0 I am going to return. Now this I am going to get 0. Now 1 plus 0. So that is 1. And that 1 will be first stored inside result of 2. See carefully. This is the beauty here. So Fibonacci of 1 plus Fibonacci of 0, 1 plus 0, that is 1. That 1 will be first stored inside result of 2. Therefore, now my result of 2 is containing 1. It is storing here. After storing, it is returning that result. Now to whom it will return? Whoever calling that function, to that I am trying to return. Means I am storing that result. After that, I am returning Fibonacci of 2 as 1. Okay. Now I am calling again Fibonacci of 1. So now when I am calling Fibonacci of 1, base condition is true. Right? What is that n value? 1. And that 1 will be returned. To whom it will return? This f of 1, I am going to return 1. Then now 1, already Fibonacci of 2 got 1 plus 1, that is 2. And that 2 will be first stored inside result of 3. Now my result of 3 containing value 2. After storing, I am returning that result. To whom I will return? Whichever function called, that function I am returning. Now Fibonacci of 3 is getting a value of 2. 2, right? So now it will get a value 2. Next, now see the beauty. Now I am calling Fibonacci of 2. Now remember, first time I have already computed Fibonacci of 2. Next, when I am again calling Fibonacci of 2, now see the beauty. What is this condition true? False. Now I am checking. Is my result of 2 is not equal to minus 1? Okay, let me go and check. Now if I go and check result of 2, yeah, it is true. It is not equal to minus 1. Its value is 1. When this value is not equal to minus 1, then you no need to compute. You straight away return the result that is present here. Now my result of 2 containing not containing minus 1, it is containing 1. Now, without wasting time, you directly return its value as 1. That is the beauty. Whereas if you see the recursion, brute force recursion, what it is saying, it is blindly going again. Same thing is again blindly repeating. Whereas in the DP, the beauty is, hey, already some fellow had computed f of 2 and that fellow stored here. Now you no need to compute. You simply take that value from there and you can directly substitute the result. That is what I have told here. See, what is the definition of that told? When you are finding solution to the subproblem for the first time. Now here I am computing Fibonacci 2 for the first time. First time when you are computing, you store that result in a table or array. I have taken array and I have stored it. Next time onwards, if that subproblem again repeats, you can take its result directly from the table or array without computing. Now you check here. Now I am not computing f of 2. I am simply going and from the table I am taking. That is the beauty. Got it? Next, 2 plus 1, that is 3. That 3 I am storing inside result of 4. After storing, I am returning that result. Now my result of 4 is containing a value of 3. Okay. After that, you can return that result. To whom I will return? Of course, whoever called that function, there I am going to return that result. Now, result of 4 will get a value 3. Okay. Next, I am calling f of 3. So next time when I am calling f of 3, now see here, friends. F of 3, now this condition will be false. Now I am checking result of 3. My result of 3 is not -1, it is 2. What does it mean? It is not -1 means initially we only set all values to the -1. But during the process of computation, someone else had already computed that f of 3 and that fellow had stored that result to 2. From -1 to he updated that value to 2. Now you no need to recompute. Don't time waste. When that result is already there, you simply go and take that result. That is what the memoization says. Therefore, now f of 3, value is already there too. Directly, I will take that result without any time waste. Now this f of 3, it will directly return a result of 3. So now it is going to get a value 2. No computation, no unnecessary things are there. 3 plus 2, that is 5. And that 5 will be stored you first inside the result of 5. After that, you return the result. Now my result of 5 finally will get a value 5. Then you can happily, whatever that value it is getting, that is 5, can be written to the main function. So main function will get a value 5. Now this is the beauty of DP. I hope is this clear? People are, some student had asked, sir, how can we take that result? This is how we can take. So please do comment here. You got it or not? So beautiful thing, friends. The very beautiful. This is one problem. Like that, many problems we'll see. And first, understand the beauty behind DP. Don't by heart. No by hearting, nothing. Simple common sense will apply to solve these questions. No by hearting. Understand the concept. From concept, we will derive the code. Getting here, right? Okay. What modifications that I have done to the recursive code? One modification that I have done is first plain recursion code I have wrote here first. This is the plain recursion code. Now, in the plain recursion code, we are not storing those results. We are not storing those results in the plain recursion code. So what we have done, I have taken this recursion code. And I have done a small modification. What modifications that I have did? First of all, okay. First, what we have done is, I have created a result array. This is for what purpose? To store the result. This is for to storing the result purpose I have taken, friends. Because I have to store the result. Then only memoization comes. Then second step, what I have done, without calling blindly this recursion call, first of all, you go and see in the table. If someone else had already computed, then you don't time waste. That is the second step that I have done. Adding, checking. This is checking. Okay, this is checking. Let us say if that value is not available, then you go and call. After calling, you please store that result. That is important. You just store that result. Okay, I have just storing this result. So these are the 3 small steps that you need to do to convert DP code to recursion code. Recursion code to DP code. Okay, so DP code, recursion code to DP code. Now, no more time waste here. Now, this is called as a top-down DP code, friends. So this is nothing but a top-down DP code. So this is the top-down DP code for Fibonacci of n. Now, top-down DP code is that. Now I need to even write for bottom-up DP code also. correct? So in top-down DP code, two things that I have told. Always remember, see, I have seen in many outside YouTube channels, they were telling wrong definition. Please don't go fall about those wrong definition, friends. So top-down DP means recursion plus memoization. Recursion plus memoization. Recursion plus memoization. Memoization. Recursion, of course, we all know recursion. Okay. Always any recursion, top to down only it will execute. How recursion tree will get executed, friends? Top to down. I explained clearly in my previous recursion YouTube live. So top to down, left to right. That is how any recursion tree will get executed. Left to right. Okay, if you see also here, how it is getting executed, top, going like this, then coming like this, then coming like this. So like this, top to down. After that, I'm going to left to right. After that, I'm going to left to right. In this direction, I'm going top to down, left to right, I'm going. This is how many recursion tree will get executed. Top to down manner, right? Okay. Now, same thing, I will explain how can we convert this into a bottom-up DP code. Very simple, friends. Once you understand top-down DP, converting into bottom-up DP is very easy. How? Let me tell you here. Okay, so in the left side, I will keep top-down DP1. Let's move all thing to little left. Okay. Now in the same here, right side, I will explain about bottom-up DP code. Now understand, one problem if you understood, now friends, remaining problems you can easily solve. Okay, so right side, I will try to write code for the bottom-up DP. That is top-down DP, bottom-up DP. Bottom-up DP code for Fibonacci of year. Fib of year. Now see carefully, bottom-up DP code. Okay. Bottom-up DP code for Fibonacci of year. Now, in bottom-up DP, what are all the two things that are there? First, in place of recursion, we will get loops. In place of recursion, we will get loops. Plus, memoization is common. Memoization is common. Whether it is top-down or deep bottom-up, the common is memoization. Memoization. Okay. Now let us talk about how we will actually write it in bottom-up. As I told, bottom-up, I use loops. So always loops value start from, so loop is always start with I is equal to 0. Okay. Or I is equal to 1, I is equal to 2. Like that loops will start, right? So similarly, whether a top-down or bottom-up, I will take one array here. I will take one array. Okay. So I'll take one array. So again, assume this size is also 100. So 0, 1, 2, 2, okay, 3, 4, 5, 6, and so on. Let us say 99. So again, I'm taking, let's say this is 0, 1, 2, 3, 4, 5, 6, and so on. Let us say 99. And again, I'll call this array as a result array. Okay. Now here, I will set all these values to, maybe you can take -1 also. You can set, no problem. All these values to -1 initially. Initially, all these values to -1 I'm setting here. Okay. All values to -1. Okay. Now here, okay. So now I will write a code. I will try to transform that recursion into loops. So function fib of n. So function fib of n. So I have taken the result array, same result array 100. I have set all these values to -1. See, I'm just writing only pseudocode. You please take care of original code. Okay. Right. Now, here, if you see in the top-down DP code, why I am writing this one? This is I am writing just before recursion call. This I am writing just before any recursion call. Just before any recursion call. Recursion call. Now, in bottom of DP, there is no concept of recursion. Therefore, this part won't come in the top down, bottom of DP. Right? Okay. Now, whatever these base cases are there, so that we hard code in bottom of DP. We hard code it. We hard code it. Like, what is meant by hard coding? So we know when n is equal to 0 or n is equal to 1, its a Fibonacci value is n. Therefore, let me try to hard code this. So result of 0 is equal to 0. Result of 1 is equal to 1. First of all, I have hard coded. That is completed. Next, this is now no more. This I have hard coded. This is just before recursion call we are writing. Now in bottom up there is no concept of recursion. Therefore, this will be not present in the bottom of DP. When this is not present, now final, we need to see how I am converting this. How I am converting like this. See carefully. Here in recursion, now try to identify what is the variable that I am using here. So let me change the color. So the variable that I am using here in recursion is n. So n is a variable that I am using in the recursion. Correct. Similarly, here also you need to use some variable. Let me take the variable is I. Here, of course, I need to traverse, right? On this array, I need to traverse. So for that, I have to take a variable I. Here I have taken a variable n. Okay, so I'm expecting this n value. Now here I am going to take a variable I. Now this I value, from where onwards I should suppose to start? I have already hard coded 0, 1 with what? This I hard coded with 0. This I hard coded with 1. Now from where onwards I need to start? From 2 onwards. Therefore, let me start I value from 2 and I will continue till where? Till 5th I want, right? Therefore, till 5 I will continue. Now I know no more recursion calls here. When there is no more recursion call, so what I'll do, I will run a simple for loop I, which is starting from 2 and I less than or equal to n and I plus plus. So what I need to write exactly here, same thing only, friends. Same thing I'm copy pasting. I'm copy pasting same thing. Only thing is here, there actually it is depending upon the recursion call. Now after copy pasting same thing, now there loop recursion variable is n. Here loop variable is I. So wherever n is there, try to first of all replace it with I. First of all, replace it with I. Okay. Because there it is loop recursion variable is n. Here loop variable is I. First of all, try to replace. After replacing this, next what we need to do here, result is depending upon recursion call. Now here my result is depending upon the array. Therefore, recursion call, you just need to replace it with the array. That's it. Story is over. And finally, you can return the result of n as your answer. That's it. Very simple. From recursion to top down, I have shown. From top down, bottom of DP, I am seeing here. Okay. After that, I will give the proper summary. I will give you, friends. Don't worry. Let me try to now execute. Now result of 2 is equal to, when I is at 2, result of 0 plus result of 1. Result of 1 plus result of 0. 0 plus 1, that is 1. Next, I will increment the I value. Then next time, these 2, that is 2. Next, I'll increment the I value. 2 plus 1, that is 3. Next, I'll increment the I value. 2 plus 3, which is 5. So once after incrementing, I loop will become faint. So result of n, 5, I'm going to return as the output. Same thing I'm getting, right? So this is the beauty here. Got it, everyone? Got it, friends, for everyone? Now let me try to put all the 3 things together and I will explain. So first we have started with the recursive solution. Let me first take the recursion solution. This is, I will put all the 3 codes in a single slide and I will give the summary. So this is the bottom of DP code. Now summary of these 3. Okay. So first our story started with the recursion code. So I will place, because this is most important, recursion code. Then our story came to the top-down DP. Then from top-down DP, okay, let me reduce its size. Okay. Then bottom of DP. Bottom of DP. This is bottom of DP. Okay, so it's okay. Let us keep here. Now see here, I'll divide this. So this is first what we have done. First we have developed the recursive solution. First we have developed the recursive solution. And we identified that this recursive solution is containing two things. One is overlapping subproblems. Overlapping subproblems. Second, it is containing optimal substructure. Optimal substructure. So we conclude that this can be solved with the help of DP. Then top-down code we have taken and we have converted it into a first recursion code we have taken. We have converted this into a top-down DP. Top-down DP. And the top-down DP containing two things. That is recursion plus memoization. Recursion plus memoization. Memoization. Recursion plus memoization. Now, how I converted recursion code to a top-down DP code. So, what are all the things that we have followed here? So, we'll see. We'll see here. First, since memoization, therefore, if you see, first step, I have created a array. First step, I have created a array. Second step, before recursion call is happening, same recursion code, before this recursion call is happening, I just created a checking, cross-checking, okay, or this checking I have done. Second step that I have done. Second step, okay, so checking. Third step, I am just storing this result. Third step, I am just storing the result. So these are the three steps that we need to follow while converting recursive solution into a top-down DP, right? Next. Third one, bottom-up DP. Third is bottom-up DP. In bottom-up DP, what are all the things that we had? So recursion, we have converted into loops. So recursion, we have converted into loops. And the common thing is memoization. So this memoization is common. Memoization is common. When this memoization is common, first step as it is, because we have to create a array for that memoization purpose, and we have set all these values to -1. Now here, this one is converted into a, okay, this one. This we have hard coded. These values we have basically hard coded. These values we have basically hard coded. We have hard coded these values. We have hard coded these values. Next, what we have done? Next, so this recursion we have eliminated and we have taken this into loops. So that is the first thing is, and this is the second step. Third step, recursion we have converted into a loops. So this recursion we have converted it into a loops. Now when you are converted into loops there, so this is recursion, we have converted it into a loops. So there the variable is n, here the variable is I. We just replaced this n to I. So there the recursion variable, here we have replaced it to I. Then no more recursion call. Previously the value depends on recursion call. Here the value depending upon the result array. So this is the summary of the DP, friends. Recursion code, identifying overlapping subproblems and optimal substructure. So from there, you need to move to DP. So from recursion to top-down DP. From top-down DP to bottom-up DP. That is the story. That is the story. So, right. So this is the one problem, and it's a complete details, friends. Complete details. Okay. Now one student had asked a question, good question. Sir, when should we use what? When should we use what? See, there is no standard mechanism, friends. I mean, maybe first you have to start with recursive solution. Of course, recursive solution, they don't accept in the interview. Then either you can use top-down DP or you can use bottom-up DP. Now, the problem with the top-down DP is the space. So in top-down DP, extra recursive stack space. So stack space we are using here, because by default, every recursion call, there will be the activation record will be created for every function call and activation record. So extra stack space we are using. So in the interview, if they said that you should not use any stack space, then you have to go for bottom-up DP. Otherwise, top-down DP is also fine. Top-down DP is also fine, right? So this is the story. Any questions for anyone? Anyone had any questions? Or tell me, is it understood or not? Tell me, friends, whether you understood this or not. Right? Okay. We'll take a small break. We'll take a small break. Perfect. Huh? Very good. Enjoying. Huh? Very good. Very good. So time is right now 8:32. So we will meet at 8:42. So let's take 10 minutes of break. We will meet at 8:42. And we will see the next question. Next question we'll see. Same story I will follow there also. There also I'll follow same story. Okay. Cool. Break till 8:42. Yeah. Hello, friends. So we'll continue. Am I audible? So someone can confirm in the chat. Okay, good. Yes. So we'll now take a new question. Now, friends, before I explain new question in the DP, so I just want to convey one point here. That is, so writing a recursive code, because any DP problem, recursion is the base that I have already told. Correct now? So we should know usually array related problems, how to write a recursive code. So that we will see, and then we will go to the next question. So writing recursive code for arrays problems. So here, let me take, and I have one array, simple. So 5 elements, 2, 4, 1, 3, 9 are array elements. Now I want to find out sum of this array. So here input, I am taking two parameters. One is input array and number of elements I am taking here. Okay. Now, how we will write array base condition? So for any recursion code, base condition is mandatory or terminating condition. So let me check simply. If n is equal to 0, if elements are 0, I can straight away return 0. Okay, if no elements are there. Otherwise, else what I'll do, I will take a bigger one, small I will reduce. That is the concept of recursion, right? So what I will do, first time, I will take the bigger array. This is the input that I have given. For me, this is the input array they have given, friends. This is the input array that they have given to us. Now, I will usually, for array related problems, I'll come from the right to left. So I will first start from the right and I will come to the left. Why? Initially, this is the array and number of elements are equal to 5. In the next recursion call, what I will do, I will take the last element. Okay. And or first I will call the recursion. That is, so this array, same input array only this time. I'll cut like this. Next time, in the next recursion call, I will pass all these array plus 9. Okay, here how many elements are there in this next recursion call? 4 elements are there, correct? Next time, what I will do in the next recursion call, so let me take the same input array. Now this time I will pass only, every time if you see, I'm decreasing its size, if you see carefully. So what I'll take, already this is there. So plus 3, and we have already plus 9. That is anyhow it is there. Next call, what I will do now in this call, number of elements are 3. Right. Next time, what I'll do, so I'll call only 2 elements. So every time, if you observe, friends, I'm decreasing its size. If you see carefully, every time I'm reducing its size. So this time I will take this one plus, already 3 plus 9 is there. 3 plus 9 is there. At this time, number of elements are equal to 2. Next, what I'll do, same recursion call, I'll call again. So same recursion call with reducing its size. So now at this point of time, so whatever this 4 plus 1 plus 3 plus 9. At this time, number of elements are equal to 1. The next recursion call, what I'll do, so I will take this 2, next recursion call, plus 2 plus 1 plus 3 plus 9. At this time, number of elements are equal to 0, no elements. So when there are no elements, I'm simply return 0 to this call. Why? For all these, if you try to add 0 also, there is no disturbance to the sum, because for any value, if you add 0, the result will be that any value only. Correct? So see how I am trying to implement. So else what I'll do, I'll call return. Okay, so same, first what I'm calling, recursion call I am doing first. So find sum, okay, comma, array, this time n minus 1 plus array of n minus 1. Array of n minus 1. So recursion call, this is what I'm doing, friends. So now if you understood carefully here, what is happening? Here? First, you are calling the recursion call. Okay, then you are calling this one. Okay, if you want to reverse also, you can reverse it, no problem. Same thing is happening. First time I'm doing a recursion call. with array. After that, I am adding this array. Next recursion call, first time n is equal to 5. After that, I am reducing its size to 4. Every time, every recursion call, its size will be reduced by 1. But the moment when n becomes 0, we are simply returning it. I hope this everyone understood this. What is happening? Please comment here, friends. I hope everyone is getting. Okay, very good. Now, so from here, the conclusion is any array related problems always start from the last element and then come to the first element. You might get a question, sir, why should I start from the last element? What will happen if I start from the beginning? See, you can start, not a problem. But in recursion, what is the property that we have studied? Started with a larger size. In the next subsequent recursion call, its size to be reduced. So first time my size is bigger, 5. Then it became 4. Then it became 3. Then it became 2. Then it became 1. Then once it reaches to 0, terminating condition. Stop. So that is the process of recursion. Same thing also we have written here. Right? So writing the recursive code for arrays problems, this is how we should follow, friends. So start with the bigger one, slowly reduce. So then we'll have to change the base case. If you are going from left to right, but if you are going from left to right, you have to change the base condition as well as you have to introduce new variable also. So you need to introduce new variable also, because to keep track of how many elements you have counted so far, introduce new variable in that case. So why this much headache? Simply with the given value itself, reducing every time, we can do easily. Why to take another headache when they have already given n? Got it? Now, next question that I'm taking is, friends, so 0-1 knapsack problem. We have already seen this 0-1 knapsack problem. If you remember, this 0-1 knapsack problem we have already seen. So what this 0-1 knapsack problem says, you take or don't take. Take or don't take. Some part is not allowed. Fraction is not allowed. And there we have seen that here on the 0-1 knapsack problem, greedy fails. Greedy fails. We have already seen also. What greedy says, go with profit by weight ratio. Go with high profit by weight ratio. But if we go like this, greedy will fail. Therefore, now let us see the DP solution. Let us see, does DP will help to solve this problem or not? So what is the input that they have given here? Input. So they have given the profit array and they will give the weight array. They will give number of objects and they will give capacity of the knapsack. All the 4 parameters is given to us. All the 4 parameters that are given to us. Now, what you just need to find out, what is the output we need to return? Maximum profit, we have to return the output. So output we have to return as maximum profit. Max profit we need to return. That is integer. Maximum profit we have to return, friends. That too, it is the integer. Integer value we have to return. Okay. See how we are going to solve this question. See, first as usual, let's try to develop a recursion code. Let's try to develop first recursive code. Okay. So how the recursion code will looks like? Function. Okay. So function. What will take? Knapsack. Let me take knapsack. Okay. 0-1 knapsack. Case I have written. So it will take input array. No. Two arrays they are given input as. One is profit array, weight array, number of objects, capacity. These 4 parameters they will give you. So profit array they will give. Weight array they will give. Next, number of elements they will give. Capacity of the knapsack also they will give. 4 parameters they are passing. Now, first of all, you need to finish this recursion call, friends. But before I finish, so if here 3 objects are there, then let me take this. To write that recursion solution also, let's try to build some logic. So for every object, there are 2 possibilities are there. Total, we have 3 objects, object 1, object 2, object 3. So total, we are having 8 possibilities, friends. Let me list down what are all the 8 possibilities. So total, we have 8 possibilities here. What are all the 8 possibilities? So 1, 2, 3, 4, 5, 6, 7, 8. All the possibilities are, let me write it here. Okay, so the meaning is 0 implies don't take. 1 implies take. Now here, no object has taken. Here, we have taken only object 3. Here, we have taken only object 2. Here, we have taken object 2, comma, object 3. Here, we have taken only object 1. Here, we have taken object 1, comma, object 2. Here, object 3. Okay. Here, we have taken object 1, comma, object 2. Here, we have taken all the 3 objects. Object 1, object 2, object 3. So apart from these 8, do you get any other extra possibilities? Do you get any other extra possibilities apart from this? No, you won't get any other extra possibility. Why? So all we have covered. Now, when this case is possible, first of all, I'm not going to choose any object. So does we get any possible? I mean, can we get any case this? When can this case will be failed? So let's try to understand. Okay, so I have taken some object. So let us say this is capacity C. So assume Wi is the weight of ith object. So or let me take object I here. Object OI, some ith object. Now this ith object, 2 possibilities are there. This ith object, whatever is there, so it is associated with profit PI. So PI is the profit and WI is the weight of that object. Correct. Object number I, O1, O2, O3, anything. PI is the profit and WI is the weight of that object. Now we have 2 possibilities are there. What are all the 2 possibilities? That is, so weight of that object might be less than or equal to capacity of the knapsack, or I'll take like this. Weight of that object is greater than capacity of the knapsack, or weight of that object is less than or equal to capacity of the knapsack. Now, when you found weight of that object is bigger compared to the capacity of the knapsack. So here C means maximum capacity. So here the meaning of C is maximum capacity. Here's 6 kg. So 6 kg is the maximum capacity. Now let us say if item this weight is 10. Now can I choose this object O3? Tell me. Let us say it is giving 1 lakh profit, 1000 rupees profit it is giving, or 1 lakh profit it is giving. But can I able to choose the object O3? Tell me. This weight is okay. I am written in the wrong. Okay, its weight is 10 kg. Even though if it is giving 10,000 or 1 lakh rupees profit, can I able to choose that object? No, you can't choose that. Why you can't choose that? Because why you can't choose is your maximum capacity of the knapsack is 6 kg, but your weight is 10 kg. So you can't choose. When you can't choose, since if your weight is bigger compared to capacity of the knapsack, okay, so does the profit is going to affect anything? And does the capacity is going to affect anything? Profit? Or does the number of objects are going to affect anything? Let me try to answer this. First of all, profit, no effect. No effect. Or in the profit, no change. In the profit, no change. Why in the profit, no change? Because you are not taking that. If you take that item, then you need to reduce from the capacity of the knapsack some value. Since you are not taking, therefore no change in the profit. Whereas in the capacity, is there any change? No change. But in the number of objects, is there any change? Yes. Why there is a change in number of objects? Because you have to ignore that and continue on the remaining variables. You should change that, continue on the remaining. For example, if weight of that object is small compared to the capacity of the knapsack, then two possibilities. Then also two possibilities, include, don't include. So here, this is don't include, right? Why don't include? Here weight is bigger compared to capacity of the knapsack. Therefore, I need not to include. Whereas here, if you see, weight of that knapsack is small. Weight of that item is small compared to the capacity of the knapsack. Then two possibilities again comes. You include or don't include. Don't include or include. If I don't include, same, whatever the things, same will get repeated here. No change in the profit. Here, there is a change. But what if I include? Then let us see what will happen. If I include, then I'll explain what is going to be happening. Now, is there any change in the profit? Yes. This profit, we are going to add it. This profit will be incremented by the ith object profit because we are including. This meaning is don't include. Don't include. This means include. This meaning is include. Okay. Now, if you don't want to include, so this will be because you are including, right? Then profit will be incremented. Whereas capacity, of course, it will be decreased. Decreased by how much? Decreased by weight of that object. Weight of that object. Now, number of elements, yes, because you are not, once you are chosen, right? So number of elements, we should decrease it by 1. So this will be reduced by 1. Similarly, here also, this will be reduced by 1. So this will be reduced by 1. Reduced by 1. Now, any doubts so far on this table? Any doubts in this table? If you don't have any doubts, then we can straight away convert this diagram into a recursion code. Okay, you got confused. Okay, so I will clear this. People, those who had confused, I will explain again, friends. These are the input array that they have given to us. Now listen carefully. This is the input array that they have given to us. That is first profit array they have given. Weight, assume this is the profit array. This is the weight array. Number of elements are equal to 3. Capacity of the knapsack is 6. These are the 4 parameters that is given to us. Now, every item had 2 possibilities. You choose it or don't choose it. Every item has 2 possibilities. You choose it or don't choose. Now, for example, assume some object has a weight which is bigger than the capacity of the knapsack. For example, let us take capacity of or weight of this object is 7 kg. But my available capacity of knapsack is 6 kg only. When your available capacity of the knapsack is small, compared to your item, you can't take it because it is hold maximum 6 kg weight it can hold. But you are trying to keep 7 kg, which is, so obviously it will break, right? Therefore, in such case, you can't include. Of course, you cannot include because, so when you are not including, then do you get any profit? If you are not including this, will you get any profit? No profit, you won't get it. So then does it going to affect on your capacity of the knapsack? No. Since you are not taking, so profit also won't increment and weight also will not reduce because you are not adding. If you are adding means then you need to reduce. Therefore, there is no change in the profit, no change in the capacity. But is there any change in the number of elements in the next recursion call? Of course, because you are not including that. So this is the first case number 1. Okay. Next, case number 2. Case number 2. See carefully. So let us say, okay, let us say. Now next, assume that its weight is, let us say, small only compared to capacity of the knapsack. Then we can happily put that item inside. But is it required every time to keep? If it helpful to maximize my profit, then I will take it. Now see carefully. Even though if it is weight of that object is small compared to capacity of the knapsack, there is no guarantee that I'm going to choose. No guarantee that I am going to choose. Why no guarantee? If it helps to increase the profit, then I will take it. Otherwise, I don't take it. Let us say this item is small compared to its weight, but is it required to take? No, not required. If it helps to get some benefit, I will take. Otherwise, I don't take it. So when you don't take it, same thing will repeat. But let us say if it is helping to get more profit, then I will take. In case if you are taking, for example, if you are taking this object, then initially I don't have any profit, and capacity will be 6 kg, and number of objects are initially 3. If you are taking, then of course I have to increment my profit. By how much I have to increment? Whatever that value of. So I will increment the profit by 28. Similarly, I need to reduce my capacity because you included that. So next, what is my available capacity? If you remove 4 from this, you will get 2. And here the profit is 28 rupees. Then what about number of objects? You got to reduce by 1. One item you chosen already. Then you are left with only 2 objects. So number of now objects are 2. This will corresponding to this. Now is this clear? Tell me, friends, now is this clear? Okay, very good. Now from same, I will apply it into the recursion code. Now from same is, I will try to write a recursion code. Maybe let me try to copy this diagram from only this part. This part I'll copy. Okay. Let me try to keep it here. Now by seeing this, let me try to write a recursion code. Okay, for every recursion code, there is a base condition. That is, let us say, friends, if number of objects are equal to 0, in my hand no objects, or capacity is equal to 0, no capacity, all items are full. Any one of these case, do you get any profit? Tell me. In your hand no objects, all are completed, or capacity, there is no space in the knapsack. No objects and no space in the capacity, no space in the knapsack. Do you get any profit in this case? You don't get any profit. So you write simply return 0. This is the base case. This is the base case. Okay. No space for profit. Yes. And no objects also to get profit. Therefore, return 0. At the end, I need to return the profit. Please remember. Now, let me write one condition. If now, see, this is the array. P comma WT are arrays. So P and P is profit array, comma W is weight array. W is weight array. Okay. Now, now I will see, always I have told we come from the last in your array problems. So now I will check weight of n-1 in case if it is bigger compared to capacity of the knapsack. Then what I have to do? See here, I have wrote here also neatly. No change in the profit, no change in the capacity, only change is number of elements. Therefore, I will write return, call the capacity again with same profit array. Profit array, weight array doesn't change because it is fixed throughout the problem. Only change is profit, any profit you will get, or in the change in the number of objects. So n-1, comma, capacity will remain same. Capacity, because no change in the profit, right? Now, if that is also false, else 2 things are possible. That one is return. If no change, I will write this as it is. I will write this as it is. Well, I am not taking this. So I will take this as it is. Either this one, comma, next what I will call. Now listen this carefully. If you understood this, then almost the story was over. 80% is completed. If you understood this. Okay, this is don't take. This is also don't take. But if I take, I will get some profit. If I take means I will get that profit. Correct? So if I take means I will get some profit. So return either this or what I need to write, either this or if I take, I will get the profit. By how much profit I will get? Profit of n-1 plus n-1 plus. Next, again do the recursion call on. Okay. Profit array, weight array, number of elements will be changing here. But this time my capacity will not be C. This time my capacity will be reduced by WI. Therefore, C minus W of n-1. Weight array WT we have taken. So WT of, I have to reduce its weight, n-1. Now see. Now see. This is don't take as it is. I have copied. This is if I take now among these two, whichever is the maximum that I am going to take, friends. Among these two, either this one or this one, whichever is the maximum that I am going to choose. Right. So therefore, I will write here return because both are two independent calls. Maximum of either this or this, I am going to return finally. So this is the separate recursion call, and this is the separate recursion call. This is the recursion call. Same thing only. This is another recursion call. So among this 1, 2, whichever is the maximum, I am going to return that as my final answer. Because at the end, I need maximum profit at the end. I hope is this clear? Is this clear for everyone? Okay. This is my now recursion call, friends. Now I have to convert this recursion into a top-down DP code. Now what I told you, take as it is this one. You take as it is this. Now I will try to convert this into a top-down DP code. So top-down DP code. Now in the top-down DP code, now previously we have only one variable, therefore one dimensional array we have created. Now here we have two variables, therefore we need to create a two-dimensional array. So let me take the result size. This time my size will be n plus 1 comma c plus 1. I will tell you why we are taking plus 1. So this will take, and you set this with minus 1. You set this with minus 1. Okay, now we have n value, we have c value. So where is this? This one. So I have to create an array. We have n and we have c. So we need to now create a result array. In this example, 4 by 7. I will tell you later why we are creating extra plus 1. Why extra plus 1? That I'll tell you in some time. So what I'll do, let me try to first create recursion code I have taken already. Outside this function, let me try to create a result of n plus 1, c plus 1, which is equal to minus 1. I take and set all these values with minus 1. Okay, that is completed. After completing what I told, friends, one thing we need to compare. That is, here n is equal to 4, 3, c is equal to 6. So 4 by 7, I'm going to create that. Here is the recursion call is happening. Before recursion call is happening, you need to write here condition checking. What condition checking we need to write? We have to check if result of n comma c is not equal to minus 1, then you can directly write return result of n comma c. Directly write return of n comma c. In case if it is not minus 1, then you simply store this result here. You simply store this result here. That's it. Over. This is the top-down DP code. This is the top-down DP code, friends. Now you might not understand, sir, what is happening here. So same thing, what we have done is like previous iteration only. First, I have copy pasted the recursion code in front of you only. First step, what I have done, result array I have taken. Second step, condition checking I am doing. Here recursion call is happening. Before that, I have kept my condition checking. Then third step, what I'm doing, storing the result. That's it. Third step. This is a step 3. So that's why I have told, if you understood the previous recursion code carefully, Fibonacci problem, these problems you can solve easily. The challenge is how you are writing the recursion code. The challenge is how you are writing the recursion code. That's why when in my YouTube live also, I have told at the time of recursion. So if you understood the recursion concept very well, DP you can understand easily. DP you can understand easily. Why? From the recursion code, it is very easy to build the top-down DP. Because top-down DP definition itself says recursion plus memoization. Recursion plus memoization. Recursion plus memoization. Correct. So this is the code for top-down DP. Next, let us see for bottom-up DP also. Let us see next, third bottom-up DP code. Bottom-up DP. Now I forgot to explain that one question. That is why n plus 1 and c plus 1. Now I will answer now. So friends, in bottom-up DP also, people are asking previous slide. So top-down DP code. Okay. Now I will answer, sir, why n plus 1 and c plus 1 I am taking. Why n plus 1 and c plus 1 I am taking. So n is equal to 4, c is equal to 6. So our result array size will be n is equal to 4 only. No? Our result array size is 4 by 7. 4 by 7. Correct. So now let me take a result array whose the size of 4 by 7. One, 2, 3, 4. 4 rows, 7 columns. Let me create. One, 2, 3, 4, 5, 6, and 7. So this is matrix of size 4 by 7. So this is 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6. Okay. Now, every column corresponding to capacity. This corresponding to capacity. That is C. Maximum capacity will be 6. Now, every row here corresponding to number of objects. Every row corresponding to number of objects. That is n is equal to 3. Now, finally, I need this value. What this value corresponding to? What this value corresponding to? I want this cell, that is, let me call name of this table as the result. Now, this result of what 3, 6 says? You have 3 objects in your hand. This 3 corresponding to number of objects. And this 6 corresponding to capacity. Now here I am listing down all the possibilities in a table. That is, here it is corresponding to, in your hand 3 objects are there and the maximum capacity is 6. So whatever that value that comes, that is nothing but a maximum profit. Maximum profit. Okay. See here. First, so if you remember when you are writing brute force approach in the previous question, we are trying to hard code these values. We try to hard code the terminating condition or base condition values in the bottom of DP. Similarly, here also let's try to hard code these values. That is, number of elements are equal to 0 or capacity of the knapsack. Basically, we are returning a value 0. Now that's 0. Let's try to hard code here. So which means this says that this complete row says that number of elements are 0. So this complete row says that number of elements are equal to 0. So when number of elements are 0, It doesn't matter, friends, whether your capacity is 0 or capacity or 1 or capacity or 2, capacity of 3, capacity of 4 or 5 or 6. You won't get any profit. Everyone agrees with that? Tell me. It doesn't matter in your hand if no objects are there, then no matter what is the capacity, 1, 2, 3, 4, 5, you won't get any profit. That is simple common sense. Similarly, first column, if you see, first column, like no matter how many objects are there in your hand, if your capacity is 0, okay, complete column, no matter how many objects are there in your hand, you won't get any profit. That is what base condition is saying in the recursion. Correct? That is what in base condition it is saying in the recursion. Right? If number of objects are 0 or capacity of 0, no profit, return 0. Same thing I am hard coding here. Same thing I'm hard coding here. Got it? Now same thing I will try to convert here. So I will take the top-down DP code. I will take the top-down DP code here. Now let me try to okay, write the bottom-up DP code. So this is the top-down DP code. Now see on the left-hand side. Now same code I will try to create a bottom-up DP code for this. Bottom-up DP code. Now see carefully how I am creating the bottom-up DP. Because if you understood this, next problems are very easy. Very easy. First, what is the story to convert bottom-up? This is top-down DP code. This is top-down DP. And this is bottom-up DP. This is bottom-up DP. Right? Okay. Now, first, whatever the values that we have hard-coded, that we need to convert it into a whatever the value that we have present in the base condition. So these are the values that are present in a base condition that we need to hard code here. So how we are going to hard code? And if you remember here carefully, here we have a variable n to represent number of objects. We have c to represent the capacity, right? So here I have taken table already outside. These values all are -1. Now if you see here, this loop, if you see, let me take, because I have to fill, I'll take a variable I to represent number of objects, because I will take, and j I will try to take to represent the capacity. So here n comma c, here I will take I to represent number of objects. Here I will take j to represent the capacity. Previously n for number of objects. Here c for capacity. C for capacity, right? Okay. Now here, if you remember, friends, so we have here n is equal to 4, 3, and c is equal to 6. So if you fix this, 0, 0, 0, 1, 0, 2, 0, 3. If you fix I, okay, so j value starting from 0 to 6, 0, 0, 0, 1, 0, 2, all are zeros only. So let me try to take one simple for loop. So this for loop, I will take I from 0, and it is run till less than or equal to n or c, I plus plus. I will say result of 0 comma I is equal to 0, which means first row, all values 0. All values 0. See, 0, 0, 0, 0, 0, 1, 0, 2, 0, 3, like that, 0, 6, all values are 0. 0, 0, 0, 1, 0, 2, like. Similarly, column also. So column also going to run for n times. So next, for I is equal to 0, this time I less than or equal to n, I plus plus, result of I comma 0 is equal to also 0. So this is first column, all values 0. That is also there, right? So whatever the base condition is there, that I am hard coded here. Very good. Base condition, I have hard coded. Base condition, I have hard coded in the table. Yes. Next step. Here we are checking terminating condition. Now this terminated condition, as I told, it will be not present in the, this will be not present in the bottom of DP. Okay. Then next, let me talk about these two things. Now, when you're talking these two, what I told here, whatever that variable, see the corresponding variable, N, I, C, J, you simply replace. Replacing, no more recursion call, array will be there. Right now, let me copy this. These two lines I'll copy. These two lines I have copied. Now, what I need to change here. Hari, this is wait array, na? WT, right? WT, wait array. This is wait array. And all WT, 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 WT. Okay. Now here also we have wait array, WT. Now N, I need to replace it by, see, try to see here. Here N corresponding to number of objects. Now same N, I have given I. Capacity C, I have given to J. So N will be here replace it to I. Their capacity C will be now replace it to J. Right? Okay. So now let me take one. First one, N, I need to replace it to I. C, I need to replace to J. Now, N, I need to replace it to I. C will be J. Now, profit weight same. N will be I. C will be J. Right? Next, this is done. Now, see, these two things you need to keep inside a loop. These two things you need to keep inside a loop. Correct? So, for now, where I should start I value from 1 onwards. Why? 0 is already completed. Huh? So I less than or equal to N, I plus plus. For J start from 1, J less than or equal to C, J plus plus. Now keep these two things inside a loop. Inside a loop. Okay. Now there will be no return. First, I have to fill the table. This is completed. Next, one more thing is pending. This also let me try to copy paste. Let me try to copy paste this also. Now, no more recursion call here. So no recursion call, friends. So what will be there? So there is no concept of return. If that is true, do this. Otherwise, else this condition. Okay. What you need to replace? I have copy pasted. N you need to replace to I. C you need to replace to J. Maximum of no more recursion call. No recursion call, friends. Only thing is array will be there. So N you need to replace to I. C you need to replace to J. No recursion call. Array will be there. So when array is there means we just required these all things are not required. So simply the result of I minus 1 because it is a 2D array. Na? I minus 1 comma J. Right? Either this or this one. So what is this says? Profit of N plus I. No recursion call. No recursion call. It will be result array of these things will be now no more. No more. N you need to replace it to I minus 1. I minus 1. Okay. Comma. One more dimension. C means J. Wait array. N means I. That's it. Only thing is replacing. Okay. Now two parameters had kept here. So one is result of I minus 1 comma J or profit of I minus 1. Okay, so let me keep like this only. So maximum of two things. These are you'll get it from array. So result of I minus 1 comma J or this one or profit of I minus 1 plus result of I minus 1 comma J minus WT of I minus 1. Among these two, whichever is the maximum that you go and update it in the result of I comma J. Result of I comma J. You need to update, right? So this loop will be over. This loop is also over. Finally, you have to write return result of N comma C. This is the final story. Same only as it is. I have taken bottom of DP and I have done small modifications here. Now this is the code for bottom of DP. This is the code for bottom of DP. Bottom of DP, right? So is this clear? Is this clear? Sir, clear, but I have to do dry run. Yeah. You have to do dry run, friends, of course. of course, you need to do it right because it takes some time to grasp it. Once you understood, it will be easy. Okay, so this video will be anyhow available in the YouTube channel. So you can go through it one more time, right? So let me stop here. So we have seen, let me quickly summarize what are all the things that we have seen so far. So far, if we go starting, let me quickly summarize. So we have seen different design strategies. Then we have seen divide and conquer versus DP. Then we have seen DP is there wide greedy. So we have seen where greedy fails. Then same thing we taken into 0-1 knapsack where greedy clearly failing. Right. Then how to identify DP problem. Then one problem we have seen to top down bottom up. Right. And then same problem we have seen it to 0-1 knapsack also. Now based on this, so let me stop here. So this is the exercise you can take, subset some problem, which is more or less similar to previous problem only. You can take it as an exercise. You just to Google it out, just to Google subset some problem. You will get that question. Maybe try on your own. Otherwise, we will discuss it in the part 2. So we will see more problems in the part 2. Okay, so that's it, friends. Thank you for all. So this video will be available. You can. When will be part 2? Not this one. This one, okay. Okay, just to revise this, you will get it. So this recording will be available in the Masai YouTube channel, Masai or Prepleaf. Any one of the YouTube channel, you will get it. You can find that recording of this. Sir, any more concepts are left, or is it tough? I discussed only maybe I would say 40% of DP is done. So many models are there to discuss. One model only we have seen. Many more models are there. Since if I cover it is too difficult, too much to take. That's why I'm stopping here. Next class next part 2 is there. So there we will talk more. We'll talk it in the part 2. Right. So when part 2 Masai will announce, they'll announce when will be the part 2. So there I'll continue from now onwards. Right. Okay. So thanks everyone. So yes. Okay. Yeah. Thank you everyone. Thank you, Srishti. So can we end the session?
Yeah, we can end.
Okay,
Thanks
you.
everyone. Thanks for joining the session.